The space elevators, a crucial stage towards the colonization of the solar system. The majority of us have used elevators frequently throughout our lives. You are aware that it is a really practical mechanical tool for swiftly and effectively moving people or objects up and down a structure. But have you ever considered what may occur if we were to construct an elevator that could reach the edge of space? Space pioneer Konstantin Tsiolkovsky first pondered this question in 1895 while admiring the Eiffel Tower and imagining that his elevators could go on forever. In science fiction? Maybe, but it's always a good idea to keep in mind that the New York Times openly derided the early proponents of space travel in 1920, calling them terribly foolish. Just before the Apollo 11 landing, the newspaper was compelled to retract a judgment with an article of apology. Therefore, pay attention to the fact that this technology, the space elevator, may soon truly astound us. The same Arthur Clarke, who with his novel The Fountains of Paradise contributed in 1979 to popularize the principle, to those who asked him for an opinion on when it would be able to materialize such a miracle, he replied 50 years after we stopped laughing about it. Since the dawn of the space age, humans have only had one way to escape the gravitational pull of our planet using rockets with top speeds of more than 11 kilometers per second. In the middle of smoke plumes, ear-piercing booms, and fire tongues, large and tiny rockets launched by controlled chemical explosions are able to transport people and vehicles into orbit. It worked throughout the pioneering era. And using rockets, we were able to launch thousands of satellites, establish a space station in orbit, and travel to the moon. Yet after the first excitement, we suddenly realized that all of this came at a very unaffordable cost. In fact, even today, it costs an unacceptable amount of over $20,000 to launch a kilogram into orbit. In addition, having to work with explosive chemicals is hazardous and uncomfortable. As a result, we are searching for alternatives, and it must be acknowledged that a variety of concepts quickly emerged, including magnetic catapults, space cannons, and launching rings, all of which we shall discuss at a later time. The space elevator, however, continued to be the most significant and cohesive of all the concepts, which NASA itself is prepared to vouch for as the tool that will eventually lessen our reliance on rockets, bringing down prices to just a few dollars per kilogram of weight taken into space. On the other hand, scientists and authors like Clarke have envisaged sending people and freight into space in capsules racing along a massive vertical cable, but up until a few years ago, it was never thought to be practical in the actual world. Hence, the only issue that remains is, are we kidding ourselves when we claim that soon, technology will be able to tackle this genuinely enormous challenge? Supporters of this really unusual technology disagree. They view chemical rockets as a dangerous, unreliable, expensive, and environmentally destructive method of entering space. And what they suggest is really something a lot simpler and more recognizable, a zip line running over a rope hung between the Earth and a substantial mass serving as a counterbalance orbiting 50,000 kilometers away. The idea may be obvious, but how can you put it into practice? To begin with, the load-bearing cable needs to be constructed of as of yet undiscovered, material that is both incredibly strong and flexible, has the right mass and density properties to support vehicle traffic, and is capable of withstanding a tremendous amount of forces that have the potential to deform the entire system. For many years, physicists, authors of science fiction, and visionaries have passionately attempted to compute the strength of these forces, only to be heartbreakingly demoralized by the outcome. In fact, neither spider silk nor Kevlar, nor even the more powerful contemporary carbon fiber polymers, are sufficiently robust to withstand these stresses. Let's attempt to learn more about it, nevertheless. The construction of a space elevator is still the subject of in-depth feasibility research. If it were to be implemented, it would be possible to launch vehicles and people from the surface of the Earth straight into space without the use of rocket engines. There are various variations, all of which share the feature that, unlike a conventional elevator, the cabin moves along the cable that serves as a guide and support rather than being pulled by it. But the fundamental concept is based on the building of a long cable with its center of mass located at the geostationary orbit, or at a distance of 35,786 kilometers from the Earth's surface, and rising up from the surface of our planet to reach outer space. This carrier wire would be climbed by cabins or containers powered by electromagnetic motors that could convey large amounts of people, goods, energy, and raw materials between Earth and space. The construction of a ground-based anchor platform is required for the realization of such a space ropeway, and the other end would be attached to a large mast located far above the geostationary orbit so that its centrifugal force is greater than that of gravity and aids in maintaining tension on the supporting cable. A tiny asteroid weighing roughly 10,000 tons that could be caught and deflected into the necessary orbit around the Earth may serve as the necessary counterweight for the mission. Imagine spinning a rope with a rock tied to the other end in a circle while holding one end of the rope. The rock is pushed out by centrifugal force, which also keeps the rope taut over its whole length. The cable in a space elevator would resemble this rope, and the rock would serve as the balance. The transit stations would subsequently be connected by 4 to 6 cables, often known as tracks, that would leave the Earth's anchor platform. Electromagnetic traction vehicles, capable of driving at speeds of the order of thousands of kilometers per hour, would go along the tracks. Such a structure would undoubtedly be particularly vulnerable to the aggression of atmospheric agents, with the crossing of the atmosphere serving as a site of particular vulnerability. It is advised to use a float the size of a large oil tanker or aircraft carrier as an anchorage platform west of the Galapagos Islands, away from the areas where hurricanes and tornadoes typically occur and with the ability to move a few hundred kilometers. This veritable Tower of Babel would be dangerously sensitive to winds. Many believe that such technology will require the creation of materials that are currently out of our reach, but whose development could take place within the next 50 years. If this is the case, the space elevator project could begin to take shape in the second half of the first century of the third millennium and be finished by the end of the 21st century. Perhaps an idealistic outlook, but one supported by recent advancements in materials science. Some special alloys that have already been created in our laboratories, like the carbon fiber nanotube structures that are similar to graphite and have extremely high tensile strength and will be used to create the load-bearing cable, already contain many of the required resistance, flexibility, and lightness properties. Consider that a nanotube wire that is only the width of a hair can even sustain a car to get an idea of what this entails in terms of tensile strength. In several terrestrial laboratories, other structures based on graphite, quartz, and aluminum are being developed and made, and testing has shown that they have mechanical strengths that are sufficient for the anticipated structural requirements. The development of materials for high-speed electromagnetic propelled vehicles and the required connecting infrastructure seems to be more difficult, although conceptually not impossible. Some have proposed an alternative strategy to overcome all these transient technological impossibilities. The concept might be to attach the cable on the moon and dangle it toward Earth to enter geosynchronous orbit rather than anchoring it on Earth. The advantage in this situation would result from the varied centrifugal forces intensities. A traditional space elevator would rotate completely every day in sync with the Earth. But a cable coming down from the moon would only orbit once every month, with a far lower angular velocity and correspondingly less distortion. Also, these forces would be set up differently. In fact, if the cable were to run from the moon to the Earth, it would pass via the Lagrangian point L1, a region of space where the moon's and Earth's gravitational pulls cancel each other out. Overall, a cable descending from the moon to geosynchronous orbit could be supported in this fashion with ease even by the strongest materials currently on the market, carbon polymers like Xylon. There would be significant savings. It would require 1/10 as little fuel to go from Earth to the moon's surface as it does now. The Obayashi Corporation, the China Academy of Launch Vehicle Technology, and Shizuoka University in Japan are currently working to find a way to develop a space elevator within a few decades, despite the fact that we are still in the domain of future dreams. Shizuoka University engineers built a scale replica of one using two 10-centimeter satellites joined by a 10-meter steel wire around 2 years ago. Cameras at either end monitored the movement of a small motorized container as it moved along the cable. Scientists will decide if the entire system can be safely replicated on a wider scale based on the data they have collected. By 2050, the Obayashi Corporation wants to have a space elevator. This would include constructing a floating anchor platform with a 400-meter diameter on Earth and connecting a 12,500-ton counterweight in space using a carbon nanotube cable. The China Academy of Launch Vehicle Technology, on the other hand, hopes to develop a functional space elevator by 2045. A form of carbon nanotube fiber that has previously been created by a research team at Tsinghua University is thought to hold the secret to producing a super-strong cable. Chinese scientists have also carried out space tethering tests, but they have kept their findings secret. Like with the grandiose and fantastical futuristic visions dreamed during the different universal expositions of the early 20th century, which were later proved to be naive illusions, all of this may appear to be simply a dream from the beginning of this millennium. The economic gain, or the enormous savings that such a realization could ensure for the space agencies, is the key distinction, though. In actuality, the extremely expensive costs of the vectors required to place the payloads in orbit are what prevents space colonization. And as we all know, the economic statement is the true driving force behind everything in a globalized system like ours, particularly in light of private enterprises' recent foray into the market. There are undoubtedly many obstacles to overcome, just as there were for those who constructed the Panama and Suez Canals, the first transcontinental railroad, or the 10-year journey to the moon. Even though it will cost a lot of money and time, it will finally be completed. Unless a better and safer alternative is discovered in the meanwhile.